So hey everyone. So the topic of today is going to be MapReduce. But before we get started, I wanted to chat a little bit about the final report. The final report, if you remember, is due April 15th. So something that can't be avoided in this class is the final report and taxes, and they coincide on the same day. At the time, that was not intentional. I hope that doesn't add too much to your stress. How many people still have to do taxes and have to worry about it? Yeah.
Okay.
Oh, you got an extension.
Procrastination wins.
Yeah. I got the best email of the day today ever. I got an email from my wife saying taxes have been filed. So that was wonderful to hear. So the final report. So it's due Wednesday at 5 p.m. before class. You have to turn in as a. So remember, this has to be a PDF turned in through Canvas. So there should be one report per group. For the intermediate report and some of the other things, you turn in 2 different people in the group turns it in. If you do that, that's okay. I'll probably be able to figure everything out, but you only need to return in 1 per group. You have 4 pages per person in the group, right? So if you have 2 people, you have 8 pages. It should be one cohesive report. So it should not be where, in some cases you can kind of have each person writes their section, you glue them together, but I don't want to have to kind of start over with kind of putting it all in my head when I get to a new section. I want one story, say, here's what we're trying to accomplish, maybe broken down to these parts, and then you have this part, then this part. That's okay. But I don't want to say, we had this one day set, we did clustering on it, we did regression on it, and then we just left those 2 things apart. I want those pulled together. Okay, I want one story for those 8 pages, or however many pages you have. Yeah?
So just a matter of clarification, so 4 pages per person, not in the thing it said that was a maximum?
Yeah, it's maximum.
Okay. And
right.
So you could obviously do less if you can contain it within that.
Yes, if you do less, I'm perfectly happy with that. It took me like all of my free time for a week to go through the intermediate reports. So it'll take me a while to go through all the final reports. So if it doesn't take you the 4 pages per person, that's perfectly fine. I don't mind that. There's a lower bound on the font size of 11. I didn't put a lower bound on the margins or the space between lines, or if you start to know the tricks, you can change the space between letters. Like all the conferences I turn in my research papers to, they have these limits, and I know all the tricks to cram space in there. Don't do those, okay? I can spot those tricks. I know exactly what you're doing. Please don't do that. There's no explicit penalty other than the font is just for a general guideline, but generally try and make me happy when I'm reading it. Make it easy to read. It's if you take the full pages, that's perfectly fine, right? But don't fill them needlessly with unimportant stuff. Tables and figures are great. Those should be if you want me to look at them, they should be within that 4 page per person page limit. Okay, so it's like, don't stress out too much about having this really long report to write. Write down what you did. The important things to keep in mind in looking for this is kind of what you did, right? So first of all, explain the algorithms you ran and how it turned out in the data and the results. So this is kind of obvious, but then I want you to try and do some evaluation of how well it worked. Okay, so unlike if you're taking the machine learning class, that mainly focuses on what's called supervised learning, where you have data and you have labels, and so then you can you always know what the label should be, and you're trying to predict the label, so you can measure exactly what you did in various ways. A lot of data mining is what's called unsupervised learning, so you don't always know what the right answer is for your data. You don't know how it should be clustered or what the right regression value is or something like that. So for some of you, you have a way of doing this. For some of you, you don't, and that's okay. I'm not going to hold it against you, but I'd like you to try and figure out some sensical way of evaluating how well you did. And that could be, we looked at it and here's what we expected it to look like, and this is what it did. And maybe take some specific examples of the data you understand. That's going to be okay if you can't do anything else better. And that happens for maybe a quarter to a third of the projects typically, that there's no perfect empirical way of doing it. And that's fine, but make some attempt to evaluate or compare the different approaches you tried, and say this one seemed to be better because of this, right? And come up some reason thing. I want to look for that inside the report. Okay, what else? Yeah, so if you look in section 5.1 of the report document, there's all sorts of other stuff that's kind of a guideline. If you're not sure what to write, there's lots of things you could try and write an answer in there. But really, I want to look at what you did and some evaluation of it. Couple more important points. I want a title for all of the reports. This will be, so it'll be more helpful when you do the poster session. You're going to have the same title. And so you're going to have, part of the poster session is each of you is going to have to go around and look at a few other posters, and this is how you're going to know which poster you're going to look at, right? So pick an informative title, and also the poster session is actually going to be open to the public, and there may be some other CS event earlier that day. So sometimes there are people who wander in from outside the class. So if you have very private data or something about that, again, some of you talked to me about this. Please let me know. It's usually only been a handful of people in the past, but you should think of, cool, this may be future employers. These sorts of people have come by before. So I have this title, and so that's important. Sometimes people forget to a title, and it just so there are other ways I'll use this for bookkeeping. The other thing is, how am I going to do the grading? The grading on these reports. So, for almost all of the class, I try and do grading in a way that's not subjective. With these projects, it's harder to do that, but I want to assign grades to them. And so for most of the project, hopefully you figured out that most of the steps, except for the report, are pretty much, if you follow the instructions, you're pretty much going to get all the points. If you went over pages, you're going to lose points for that because I have to read more. I take points off for that. If you turn them in late, you may lose points, right? So for the final report, I'm going to have some aspect of grading because it's clear some people put in way more effort than other people, and I want to try and reward those people. And so basically, there kind of roughly be 3 levels. So this is out of 50 points. So 45 points is going to kind of be the meets expectations. So if you've basically done all the stuff I've asked you to do, and I said, you propose some things, I say you basically just need to do these few things. You do that, you'll get 45 out of 50 points. Really, that's 95 out of 100 points on the project. That's still like an A mark for the class. If you do more, 50 points would be above expectation. And then 40 or less is this was something below my expectation. Okay, so it seems like everyone on the class, just about everyone at their intermediate report, I gave you guidelines where how to easily get to this meets expectation, and it was clear some of you are already on a pace, well past this. Okay, so this is roughly the grading scheme. it will be a little bit subjective, but I hope you realize that there's needs to be done for this part of the class. Okay, so any questions about the final report that's due Wednesday? Okay, great. Yep.
So this is just, I mean, what are some of the things that you've seen in the past that were just like awesome projects? Or have none
Yeah,
met your expectations?
Well, no, it's usually about like a third of the class will get up in this range, right? It's just so off the top of my head, like what are some awesome things? I mean, it can vary from. It's that you're asked to. I kind of say asked to do a minimum, implement, compare these algorithms, and you go well beyond and do a bunch more things on top of that. Or you kind of do the basic day mine techniques, but in order to get there, you had to go through a lot of struggles with the data for one reason or another, and you really made it through that really well, right? Or you had some, there's some people who have done things that was maybe a third of the way towards a research paper, right? They took some technique and they said, here's a new way of doing this, and they came up with a new way of doing it. That was something that I could see had potential to turn into like a paper at a top conference in this. And those are the sort of things that are going to get up in this 50 range. It should not be for anyone in this class can make it up there. It's not something that only the PhD students can make it up there. Anyone can make it up there. It's a matter of I just want to reward people who've put in more effort than other people. Where it's very clear that you really did some cool stuff, and it's not always effort. Sometimes it's, cool insights. This is more of a reward. This is what you should. This is kind of if you did what you're supposed to do, you get 45. That's still an A. It's great. If you did less than what you're supposed to do, that's when you start getting to 40. And look, it's even if you did a little bit less, 40 is not so bad. It's 90 out of 100. So. Okay, but I should have some cooler examples on hand. I'll try and on Monday next week you have poster drafts due, and so next week on Wednesday I will bring in some pictures of old posters that I thought were cool, and that'll give you a little bit more insight. But you probably haven't even started thinking about posters yet, so I don't want to talk any more about them now. But okay, so cool. So, another question.
With the posters, are there dimensions?
Yeah, so it's written in the project document. There's a couple of details I need to update on how you'll turn them in, but it's pretty much what's said in there. There are a couple of I might change a little bit of the details, but I'll do that by next Wednesday. But if you'll turn them in by next Monday, you'll have essentially 2 days to do possible revisions afterwards for given feedback, and then the department will actually print all the posters. They're going to be 2 feet by 3 feet, so they're not huge. If you want to do something beyond that, you can print it on your own. But the department will print it, and we'll have poster board and stuff set up at 2 feet by 3 feet. And the plan is essentially to have it here or maybe out, plus maybe out in the hallway. But I might end up moving it, so I'm still working out those details. It's going to be really tight in here and get really hot too. But it should be a lot of fun. So it's a lot of stuff going on. Okay, so let's see. So the topic of today is MapReduce. Okay, and so who's heard of? So who's not heard of MapReduce before? Okay, good. So who took this class largely because we were going to cover something about MapReduce in it? Okay, so like in the past, what's interesting, the reason I asked that is because in the past, something like half the class, that was the main reason they took it. This topic, I still have it in here because I think there's some really important takeaways from this, but it's become much less of a buzzword over the last few years. At some point, I thought of really extending this session of the class where we would do much more with MapReduce and fleshing this out. But it's a real pain to actually have stuff where a class, especially this size, can actually do really interesting stuff on MapReduce. You really need to have a huge scale of stuff to do it. Okay, so just a little bit the history before we start. So MapReduce is this software. This is proprietary. I can't spell. I'm going to use it. So this is man. Okay. Third time's a charm. So this is Google specific software. So you can only run MapReduce inside of Google. It's a code base that they built, and they wrote a paper on this in like 2004. So there's an open source version of this. And the open source version is called Hadoop. And this came out in 2008, but it wasn't really that stable until 2010, really. So somewhere around there. It became increasingly more stable. Okay, so in 2004 they came out with this. It was published, I forget in which conference it was published. I think it didn't get it. It may not have gotten into the first place that they tried to publish it. Most of the research community didn't know what to think about it. In fact, some people flat out said this is a waste of time. And then this Hadoop came out much later. It took them a long time to figure out how to write Hadoop, and that there was really a need for doing this. It turned out roughly from 2010, say till 2000 and maybe 13, there was like a huge kind of explosion. All right, other words, bang, whap. There's a lot of commotion about this MapReduce, especially in the Silicon Valley. Companies, if you wanted to deal with all sorts of data and scale up very quickly, you're supposed to do using Hadoop. It was people were building it in the cloud. This was if you're doing stuff on the cloud, you're doing Hadoop stuff on the cloud maybe. This was very much a big deal. There were certain, but this Hadoop, this open source software had certain kind of limitations to it. People tried to apply this to everything. Okay, what happened afterwards, and this started probably already in 2010, is there were many kind of specialized variants of this that handled special cases that people tried to do for Hadoop. For dealing with graphs or for dealing with certain types of analytics. Around 2013, I think it's only becoming more stable. Maybe in 2014 is when this really became stable. There's a system out of a research group in Berkeley called Spark. And we'll talk about this. This kind of fixed a major kind of issue with how the implementation of MapReduce and Hadoop was working. And this was really fundamental to it. It was not an easy thing to fix. It took some really smart people to actually build this new system, Spark. This is now often distributed with the main distributions of Hadoop. And so a lot of people are using this now, or these other specialized variants that handles special case of data problems. Okay, so it's still very important. There's a lot to be taken away from these. These specialized cases are doing things you could do in MapReduce or Hadoop, and you may not have realized they would have done them unless people studied this so carefully. And what's really came out of this, and I'll kind of describe this in more detail, is there's this distributed file system, which was the backend for this. In Google, this was called the Google file system. In Hadoop, this is called the Hadoop file system, the HDFS. All these specialized variants, or most of them, are somehow built on this HDFS. And this has survived to some extent. Spark kind of, to some degree, is getting away from this. But there's still some elements of it in there as well. So why was this such a big deal? It kind of has to do with there's this kind of notion that two things happen at the same time. There's this MapReduce was kind of equal to this other buzzword, which is big data. This kind of exploded at the same time. Big data is still a buzzword that's going strong. There are things being indoctrinated with this word in it, so it's probably going to last. There are journals and conferences and stuff, so we probably aren't going to be able to get rid of big data. MapReduce might fade away. But there was this relationship between this, and kind of the big reason I see this is MapReduce was well equipped to handle certain aspects of big data that previous ways of dealing with data were not able to do. Okay, so what? So there are kind of two aspects going on here. So one is that the data is enormous, and so by what's meant by this is it's going to be, like what this means keeps changing, and so this might mean several terabytes. This might now be too small. Terabytes might be the wrong scale to look at this. But it needs many, and this could be 100 to 1,000 machines, and not to compute something, to store the data. So you're going to need hundreds of hard drives or sets of hard drives on each machine to store the data. Okay, and maybe you don't do hard drives. Maybe you store it in Flash now. Is been one of the movements. So if you're doing this kind of, I operate kind of in this academic setting where often I don't have access to hundreds or thousands of machines to do experiments, and it's kind of hard to always, most of it is in setting that up. You can kind of simulate some of those experiments on maybe tens and on like dozens of machines. So if I have 16 or 32 machines, I can kind of simulate some of the effects, but I'm not really getting all the advantages until I get to 100 or thousands of machines. Okay. So the other thing is that data was often fairly static. So it's not changing that much. It's usually the only changes are when you append things to the data. So basically you're reading what's happening on your website, and every time something new happens, you write it onto the end of the data, but you're not really updating the old data much. The old data is just sitting there, and it's staying on the computers. It needs this many machines to store the data, and you aren't going to keep swapping out it from these machines. You're putting it on those machines, and you're leaving it there. Okay, you're leaving it on those machines, and then you want to do something with it later, right? This is all the data your company has collected. You then want to go in and analyze this data, but you're not keeping kind of swapping it around, or you don't get new data. You don't want to pay for the cost of putting the data on the machines as the first step. You start with it there. Okay. So there are other aspects of this. If you look at the big data trends, there are these 3 V's, and then there are 4 V's and 5 V's, and some of them were like the velocity of the data. This is kind of something that's orthogonal to this MapReduce view. There's also these things where there's lots of variety in the data, and we'll talk about that as well. So the data could take on lots of different kind of structure to it. That was also something that came up, but that wasn't really, I think, one of the core issues. Okay, so and then these patterns of the data, kind of, there was a similar thing that also happened at this time where the way people thought of kind of doing scientific exploration changed, right? So there was this change from classic science to what's called data science. Okay, so classic science was you make some hypothesis. Okay, you have this thought bubble hypothesis. You go and you gather some data. So this would be like you're a scientist. You say, I think fruit flies are going to live longer if I feed them only like Cheerios or something. So then you go and you take a bunch of fruit flies. Some of them you don't feed them Cheerios, some you do. You collect the data, right? This is the gathering data phase, and then you try and do some evaluation. So you say this hypothesis was supported by the data or is not supported by the data. Okay, and if it was not, then you go back and you modify your hypothesis and you repeat. If it was evaluated, then you kind of then you like write a paper or something, And so this is like basically 100 years old. This is how we've done statistics. All statistics was built to do these sorts of questions, right? Science was built around this process. But now, since we have this data, we don't need to go and gather data. We start from the data that exists on the cloud someplace, and then you go and you kind of mine these patterns. And then, if you found a pattern, then you go and you write, the paper that you send to, Nature or Science or someplace, right? So this is kind of this data science, this new way of doing science. It's also often how a company would analyze its old data. Sometimes they still set up these experiments where they say, I think if I kind of made the background of my web page white instead of yellow, the customers are going to be happier, right? So and so what they'll do is they'll sometimes show white, sometimes show yellow, and do these tests, right? So they'll sometimes still gather experiments like this. So in fact, I don't know if you remember the web page for eBay used to have a yellow background, and this was a very kind of characteristic part of eBay, and they realized that this made people think of this wasn't. I didn't always put people in the right mental state, so they wanted to change it to white. So they did it kind of very gradually over like 3 or 4 months, where they gradually changed the background color. Anyways, it's completely unrelated to this. But so this new way of doing data science was kind of taking over science, and it was a different way of analyzing data. This class is kind of about this middle step in here, right, where you have the data and you somehow want to mine patterns of it. This could be doing regression or clustering. It could be all sorts of things in here. But you had this big data. How do you get access to it if it's so huge that it's on hundreds or thousands of machines and it's not changing so much? You're only appending it. And so MapReduce was a system that kind of made this available. Okay, and so this kind of happened at the same time, and that's why kind of in the early 2010s or so, this really took off. A lot of companies wanted to do this with their data, and MapReduce was or Hadoop was the default system of how to do this. So this is one of the reasons why this kind of took off. Hope you realize that this step, like this had been done for 100 years. Statistics is really well understood, even though a lot of people in science don't do statistics right. There's a lot more questions here about the right way to do this, where you're not gathering data specific for your hypothesis. All of statistics has some kind of major issues going on with multiple hypothesis testing and so forth, but it's a whole nother discussion. I would teach a class on that if I knew the answer to that. But that's not really understood the right way to do that right now statistically. That's an unspoken thing about a lot of science right now. Or it's spoken by some people, but most people ignore that. Okay, so how does so let's get to how does this MapReduce or Hadoop work? And like I said, one of the last things of this, and this is where we'll start, is the specific distributed file system that's used as the backend. How is the data stored that makes this system possible? And so flexible and resilient. And inside of Google, this was called the Google file system, and inside of Hadoop, it's the Hadoop distributed file system. And this is basically the same thing. So there's kind of a hierarchy of things are stored, and it's fairly flexible. So at the bottom, all data is stored as at the item level as these key value pairs. Okay, so every piece of data. So like think of like if you're writing something like in a JSON format, then you kind of have the label associated with it, which is well, actually the JSON format is not a good idea. It's not a good thing. So it is not the right comparison here. But you have some sort of key describing what the data is, and then you store the actual data. Right? So you can think of this many different ways. So you can think of the key and the value. So for instance, the key could be if you have some log, maybe you visit your website as some log, you have the log ID number as the key, and then this is the actual log is stored in the value. Right? This key should be some sort of unique identifier. Right? So if you have a web page and you want to do PageRank, then either this is going to be all the links on the page, and maybe also all the HTML of the web page, what's actually stored there. So maybe you store objects of the graph, or you store certain summaries of HTML. Maybe you turn this into n-grams, or this bag of words model. You've extracted some other properties of this. You may not need to store the full web page, right? But this web page, this could be the not the IP address, the web address of the web page. So if you have, if you're looking at more general documents, it could be the document ID, and maybe saying that it's if it's in some certain set, then also a set ID. So you have some set of documents, say it's the Wikipedia set, and then you have the page within Wikipedia. That would be together would be the key, and then the value is the actual text, right? And you could also think of this as like if you're building an index. So this could be the word of it that you would index, and then or the word on a corpus, and you can say, and this could be which pages it appears on. Okay, so kind of you're thinking of fairly, this value can either be fairly can be fairly free form like HTML, right? Or it might be very specific, and we'll see some conditions where we say something much more specific, like the value ends up being like a single number, but the key needs to be some sort of unique identifier. And so this is initially how you're storing all of your data in this way somehow. Right, so if you have a file system, maybe it's as simple, like any file system is like this, there's some kind of memory address of any file. And so that can be the key, and then the file is the value, right? So this is not really something all that new, but we're going to think of all of our data following this form. Okay. Okay, so this key, this is kind of the back-end storage of the key. Should mention, we'll see some examples where you can have multiple things with the same key, but this will usually be some intermediate representation, and that'll make a bit more sense later. Okay, so the next part of this is, the next level of this is the block level. Okay, and so this is basically these key value stores. If you have so much data that fits on it needs hundreds of machines, you're not going to store this as a single file that has all these key value pairs in the same file. What you're going to do is you're going to break the data up into blocks. So each block usually has some size. A common size is often something like 64 megabytes. Okay, this I've seen in literature that this is a common size, but you can go into the internals and you can set this differently for various ways. But basically, you take this huge set of these key values pairs. Think of all the web pages out there. You break it up into blocks of this size. Usually, a single value is rare for it to be more than one block. You think of multiple values inside of each block. It's kind of how you think of it. So this should have multiple key value pairs inside of each of these blocks. Okay. So the other thing is that now each block is going to be replicated 2 to 3 times. So each block you're going to store 2 to 3 times in some different locations. Okay, so whereas the key value, but you only replicate on the level of the blocks, and these are and also not local. Okay, so this part is kind of when you first see it, should be the most unintuitive part. If you've taken a data structure class, you think if you have this big list of key value pairs, maybe you're probably going to want to sort them by key, and you are going to store the things with similar keys next to each other. So inside of each block, you may have similar keys. Okay, but across blocks, you don't want to store neighboring blocks next to each other. So not local, this means sorted neighbor blocks are going to be on these are going to be on these are going to be stored on some different machines. Okay, so this part is kind of strange. Let's build a new page here. Yep.
Over here. So, could you just re-explain self-neighboring blocks? So what I guess my question is, what you mean by that is, so we replicate this 64 megabyte block times, and then we're going to store those other 2 blocks somewhere else. Is that what you mean by self-neighboring ones?
Yeah, so let me draw a picture here, right? So all these key value pairs are stored in this list here, right? So think of this as my full data set. What I'm going to do is I'm going to break it up into these blocks, right? And each of them are about the same size. They're each about 64 megabytes, right? So this is the 64 megabytes, and then I'm going to have my different, like all my different machines out here. And so I'm going to put let me draw a few more machines. So I'm going to put, I'm going to put the blue block here, here, and maybe here. I'm going to replicate it 3 times. The red block, it might be on the same machine, but it does not need to be on some neighboring machines. Right? I don't need to have these next to each other, right? And in fact, it's probably going to be that I have hundreds of machines. I'm probably not going to have 2 blocks which are next to each other on the same machine. It could be, but I'm going to not intend to do that, right? And so I'm just going to keep loading these blocks up in these different machines. Yeah.
So the amount, So the replication rate is dependent upon how many nodes you will have. Because the higher amount of nodes you'll have, the more success you'll have in failure, therefore you want more replication. Is that
Yeah, so, people usually do 2 or 3, and it depends on kind of how stable they think their system is or how careful they want to be about the data. If your system is not that big and you only replicate twice, you might have 2 machines go down that have the same data on them, and you might actually lose that data. It's fairly rare, but it could happen. If you have 3 machines, that's much less likely. But when they first did it, I was hearing the number 3 was a common. Now it's much more likely to be 2. I guess things have gotten more reliable, and they've gotten bigger as well. And I think that kind of evens things out a little bit. But usually 2 or 3 are the numbers I hear. I've asked, like, do people ever do 4? And I've never heard someone even does 4-way replication. Maybe on very critical data, you would do something like that. Okay, yeah.
It might also depend on how your network is segmented out. If you're doing something
Yeah.
like Amazon, you have, miles and miles.
Yeah, that's some places where they do this. Like a lot of these companies, like Google, will have many different data centers, and each data center will have 2 or 3 ways replication. Every place that they have local computation, right? This is for doing computation. They are going to re-replicate it 2 or 3 times. So that's probably also true. So that could be within a single data center. They're using the same data for multiple tasks at the same time. They might replicate it more, just completely double the data within there. That could be possible if those are really highly accessed over and over again. But within this is like one system setup. Yeah. So this is what I mean by it's not. So this is where it's kind of not local. All the locality you're going to get locality in 2 spots. So you're going to get locality inside the blocks, should be local. And then when you're doing this mapping and reducing, there's going to be another step. The mapping is going to create new sorts of locality. That's the other place it's going to happen. And I'll explain that a little bit. I'll get to that soon. So we kind of touched on this a little bit, but this non-locality should seem very strange to you if you haven't seen this before. But what are reasons why you would actually want to do this? Like, why would you want to kind of make these blocks not local to each other? They're in stored on completely different machines. Yeah?
Process in parallel.
Yeah.
One machine works on the data, one other machine works on the data, and if they were right next to each other, you couldn't do that because that machine would have to process one and then process the other.
Yeah, so if I wanted to do, that's not even close, so I spelled parallel. Okay, sorry about that. Okay, parallel. Okay, so if you want to do stuff in parallel, maybe the part of the data you want to do it on is a subset of the data. Maybe it's this part of the data. Well, if it spans across these 2 blocks, if all the blue data and all the red data was all in the same machine, they're only 64 megabytes. I could fit them on there. Well, I'd have to move them to other machines before I could start doing stuff in parallel. So the data is already split up, to some extent. So it's kind of natural to do stuff in parallel because the data is already on different machines. It may limit what I can do in parallel, but it's already split up, which is useful for that. So what's another reason?
Redundancy of data.
Yeah, so this is one of the major reasons. So this redundancy of the data is because when you have this many machines, so it's much more common for stuff to go wrong. Like who in this classroom within the last So let's say since the start of the year has had their computer die on them. Is anyone? Okay, you don't have to. Okay, I've seen enough hands. There are a few people who have hands who've had their computer die on it, and you don't run it nonstop all the time either, right? A few people have had this happen, but when you have thousands of machines, you get computers dying like all the time, right? So what happened is you're trying to do some computation, and all of a sudden you're trying to do it on this one with this red and blue block, and this one goes down. I want to have another computer with the data already loaded on it. Or if the hard drive crashes, I don't want to lose it. It's backed up in these other places, right? So this borrows from ideas from like doing like a RAID across multiple hard drives. But now you're doing it over the cluster of computers as well. So it's not just that the hard drive fails, but maybe some other aspect that you can't get it off of the hard drive for whatever reason. Maybe the motherboard fails. You can go get the hard drive and swap it out, but that's going to take a long time to do. Typically, when a machine goes down, these big clusters, what they do is there's some guy's job who they visits every machine once a day, and if it's down, it's rebooted. So they don't necessarily even reboot it immediately. They wait until the end of the day to reboot it. So that you want to have the data backed up someplace else. It could also be that it's not just that it goes down, but it just gets really slow. Maybe there's some process running on that computer which just causes it to grind to a halt. You don't lose the data, but it's just running really slow. You want to be able to say, this one's running really slow, so I'm going to shift the computation out to this computer and this computer. And the fact that the red and the blue block, even if it doesn't matter if they're next to each other, even if they're stored on the same computer, they're probably not stored together anyplace else. So if this was the last part I was waiting for, then I want to recompute what this guy was doing. I can spread it out in parallel across many different computers where this data was also stored. Yeah, but this kind of, these slowdown or these computers dying or crashing was really a big problem when you try and scale stuff up. When you deal with like the other version instead of MapReduce kind of expansion was these people were buying these supercomputers, these really powerful machines that were very individually expensive to try and really guard against them failing. They still occasionally failed, but they're much more resilient to failure. But then because they still might fail, you had to put in all these steps to try and recover it if that happened. And this was just simpler, right? You just had some system that if this one went down, you rerouted the computation to another computer with the data, right? So the other reason is heterogeneity. So if the data could be fairly diverse and different, and doing this allows for that, right? So you may store many different types of data. You may have logs in your system. You may also have web pages. You may also have different sorts of customer information stored on here. And because you kind of store them in these blocks at random, this 64 megabytes seemed to be a reasonable size. You can store many different data sets in some sort of key value pairs, and it could go, and you could store it in different ways. So maybe I have a lot of blocks stored on this computer, but when I do a process over this part of the data, only a couple of them are on this type of data. So even if my data was very heterogeneous, this was flexible and it didn't kind of put all of the same type of data in the same location. Right, so this was kind of not very intuitive, but it turns out you can still do a lot of computation easily, even though you've stored your data in this way. Yeah?
So does that mean each block has to be the same kind of data? They all have to be around?
No, that's not true. Yeah, so like this one, if you look at these could be all pictures, these could be documents, these could be log files.
Just inside a block?
Usually inside of a block, you have it all the same thing. Yeah, so you think of it's local within inside of a block, right? It doesn't need to be, right? You could have multiple types of keys, and if it's not the sort of key you're looking for, then you just skip over it. But typically you would have these be congruent, items from some larger file that you split up. So think of them as if you're transferring data from disk onto memory, usually move it in blocks. I think they're usually much smaller than this, but the same kind of process works here. Okay, so this is the back end, and this part is really kind of stuck around. A lot of these big systems use this because it allows you to do stuff in parallel. It's very redundant, or it's resilient to all sorts of things that can go bad, and it's very flexible in the sort of data it can handle, independent of how you're going to process it next. Okay, so how does this MapReduce work? How does it work? Well, it's going to do basically two things. It's going to map and it's going to reduce. So that's the simple answer. But really, there are kind of some other steps inside of here as well. So it's going to have a map phase. It's going to have a reduce phase. And then I'll kind of fill each of these in. So this map phase, the job is to go from these key value pairs into these other sorts of key value pairs. And it may be one key value pair maps to a set of these key value pairs. Okay, so for each key value pair, I'm going to treat this as an individual object. I'm going to write a function that looks at one key value pair and outputs another set of key value pairs. Okay, so this is maybe step 1 here. And I'll describe these and then I'll go through several examples. So just kind of hold on to your hats a little bit. This next step is called the shuffle. And this part is not something that you write. You write the mapper. You write this function. The shuffle, what it does is it puts all output of these key value pairs as the output in here into this part onto this onto the same machine. So each machine is going to do this mapper in parallel. It's going to read their key value pairs on their local blocks, one block at a time. It's going to create new key value pairs. Then the shuffle is something that takes these new ones and says everything with key 1 is going to be on a certain machine. Okay, so if I have, you can think of starting as having these machines. So this is machines like this, and they each have data, right? And so if you look at this one machine, it's going to output key 1 and value 1, and say key 2 and value 2, and it's going to have a bunch of other stuff. And so this one is going to get this. This one's going to get everything with key 1 in it. Key 2 is going to be here, so everything with key 2 is going to go onto this machine. Okay, so you're mapping. So this shuffle is after you've turned out your key value pairs into new key value pairs. Sometimes sometimes this map is just the identity map, right? If you have them stored in a nice way, think of the original ones. Then the shuffle moves them from one machine onto the other machine. So then if this machine also gets, say, key 1 and V4 and key 3 and V5, then what happens is this one is also going to shuffle over to here, and this one's going to go to this other machine associated with key 3. Right? Yeah?
So it's kind of the opposite of a shuffle and more like a sort.
Yeah, right. So you should think of more like a short, like a sort instead of a shuffle. It's what's going to happen. I guess the reason they call it a shuffle is because usually most machines will send stuff to almost every other machine. So if you look at like these shuffle networks, then you're going to kind of be sending stuff all over the place. So you could think of it as a sorting. In fact, sometimes one common way how this will work, and this is not always the case. I mean, there are kind of two ways where this is work. One is that it just creates a hash function across all of these keys. And so it just, for every key, it hashes it to one of my different, an index associated with each machine, and it sends it there. The other way is it actually does a sort. It kind of has an ordering over all the keys, and it breaks them up, and it sends the first bunch of them here, the second bunch of them here. You need to make sure not to overload keys, because this may not have an even distribution. So it again uses tricks kind of like with sampling and hashing to make sure it doesn't overflow. So remember from the very first lecture, if you sample keys and then you sort like a subset of them and you sort those, and then you say, those are going to give you about an even distribution. So maybe if you have 100 machines, you sample something like 5,000 keys, you sort those, and then you evenly space, and then you kind of pick every 50 keys to indicate a region that goes in between. Like this maybe key, like 51 through 100 gets mapped to this machine. And this is how you do sorting. And so for a while, the best, actually the fastest sorting algorithms, there's this TerraSort kind of competition every year. For a while, when the first systems of Hadoop came out, the fastest sorting algorithms were doing this, and they were doing it through Hadoop, because it was the only system that could scale up to enough machines. And they kind of used the sort built into Hadoop to do the basic sorting, and then they kind of tweaked it to all ways to kind of get the best performance out of it. But that's one way how this works. Okay, so this shuffle kind of, once you have these new key value pairs, it matches all the things with the same key on the same machine. And then this reduce function is going to be the third step here. And what this is doing is it's somehow kind of combining all of the values with this the same key, right? So you can think of the input is something like a key and a whole bunch of these values, v1, v2, v3, up to say vn, and the output is going to be is again going to be a key value pair, is key prime, and some function of k, and then this set of these values. And this function, the output of this function might be multiple keys, but key value pairs may just be one key value pair. Okay, so this is kind of the whole system here. Yeah.
Does it ever happen that you have to like implement your own shuffle function for a special kind of data, or your own comparator for sorting?
So in most cases, no. The whole point of the design is that you don't have to implement shuffle. This is one of the really complicated steps that is heavily optimized by the Hadoop or the MapReduce code. But it's like some people will always want to write their own version of something, and you can go in and you can edit this code, right? And so I've been on some research papers where we wanted to do something a little bit different, so we went in and edited the code for the shuffle to do something else. So you can do this, but you're not supposed to do it. It's supposed to work like magic. You only write the map function and this reduce function. And both of these are often very simple things. They can be like one line of code. Yeah.
So it's like a really, really big hash dictionary, only you have to come up with your own ways of making the hash and dealing with collisions.
Yeah, right. So you kind of need to come up with some way of some task you want to do, convert it into a map function and some reduce function. You somehow need to, it's a different way of thinking about how to write code on stuff. And it turns out a lot of types of problems you can fit into this paradigm. And for some period of time, like in the last decade, there was a lot of research on how do I do problem X inside of MapReduce, because they thought the future is MapReduce. Let's do everything in MapReduce. right? And so that led to some interesting research, and some of it is still useful, some of it survived, some of it was forcing problems onto a certain model. Okay, there's one more stage here I want to squeeze in. There's sometimes something called, so write this as 1.5, and this is called the combiner. And so if this set here has several keys with the same, you take your one block and it outputs a whole bunch of key value pairs, and some have the same key. Well, you can combine those before you send them. Okay, so let's say that you have, for example, you'd have key 7 and the value 3, and you had key 7 and the value 8, and your goal is something like to compute some sort of sum or something, then you would do something like key 7 and the value 11, and then you would map it, and then you would call this step the shuffle step. And so then you're only sending one key value pair instead of two. Sometimes this can be many more. And I'll give some examples where this is really necessary. Otherwise, the shuffle step will really overload the system, and you can really, or even this reduce step becomes not possible because you get too many key value pairs sent to the same reducer. So sometimes you can do some basic, and often this looks just like the reduce step. It's not always true, but often the same thing you call for the reducer, you call before you send it off of the mapper. Right? So think of this as one machine on the mapper, so you call the map step here, and then you call the reduce step down here, and this middle step of sending it is what's happening in the shuffle. Okay, now in practice, the map machines and the reduce machines are often the same machines, right? So you're not sending it down here, you're actually, you're doing some routing. This guy goes over here, as well as this guy, and this guy goes up here, and this guy goes up here. So they're not two sets of machines. There's one set, but it's prettier to draw pictures to try and look them as two sets of machines. Okay. So this is basically how it works. This is it. You basically only write the mapper, this reducer, and sometimes also this combiner function, but often this is just the reducer. Sometimes the mapper is just the identity. Sometimes the reducer is one of a few common reducers. So you don't have to rewrite something. It ends up being you get to do these huge amounts of data movement without having to write very much code at all. The shuffle step is somehow doing all this for you. Yeah.
Once you've done the map section, you take those keys, you move them back into blocks, and you transport the blocks, or do you just?
Yeah. So how it does the shuffle is kind of done under the hood. It does move them. Kind of, you're moving this across the network. The network tends to move stuff in. It works better if you move it in blocks of certain sizes, and different networks are optimized for different blocks. It's not necessarily the same as the HDFS block. Yeah. So yeah.
And also, when the keys get back to the other side, do they just file them back in the Hadoop file system, or do they just keep them in memory?
Yeah. So this is actually a really good question. And the first few years I was reading about Hadoop, I didn't really grasp the importance of this. But the question is, what happens once I produce these keys at the output of this reduce step? Do these stay in memory, or do I write them back to the file system? Well, there's some part, maybe I want to do some analysis on this. So I want to look at them once I have them in memory. Maybe I do visualization, or I do some querying on top of them. But in general, after I do that, I write these back. I write the output here. These go back to the HDFS. Right? The output of the reducer goes back to the HDFS. This happens every time you call map and reduce. Okay, so if I'm just doing it once, you're like, okay, that's not a big deal. I want to get these output keys. I call MapReduce, map shuffle reduce. Then I get these keys. I look at them. I draw some conclusion. I go and write I go and tell my boss I did something cool, and then in the background it's writing them back to HDFS, right? But sometimes you want to chain a few of these things together. You want to do a map, shuffle, reduce, and it takes you a few rounds to do this, right? But in between the rounds, it always writes it back to HDFS before it starts the next round. Okay? This seems like, okay, well, maybe it doesn't really need to do that, right? That seems kind of wasteful. If I'm going to do like several, like 3 or 4 rounds, I probably don't need to do that. Well, it turns out, people were not able to fix this in Hadoop. If you don't write it back to HDFS and a machine crashes, it can't recover. Right? It needs to write it back to disk in order to have all these resiliency properties of the HDFS. Okay, so this is necessary to write it back to disk here. It seems like, okay, maybe you should be able to get away with it, but to do crash recovery on this sort of stuff was really complicated. This writing back to disk is what was avoided in the Spark system that I mentioned at the beginning. So the Spark, it figured out how to avoid writing this stuff back to disk in between rounds. Okay, so, and this caused a major change. So if you think of some of the algorithms that we wanted to run in class, say we had a huge data set and we wanted to do k-means clustering, so we wanted to run, Lloyd's algorithm, right? How would you run Lloyd's algorithm inside of MapReduce? You'd have your data, and what you would do is you would store on each of the machines the centers. You would map every data point onto a new key, which is the center it's closest to. You would send all of the values, which are the data points, with the same center to the same machine, and then you would take the average of them. And you'd calculate new centers, and you'd somehow distribute these among the machines, and then you'd repeat this, right? This takes, maybe that you run this for 20 steps, right? This was really way too slow in MapReduce. If you look at some of the first examples of MapReduce, people are trying to figure out what is this, where are some examples. When it was first coming out, I looked up, said k-means clustering. This was someone wrote a blog post, and they said, here's how you do Lloyd's algorithm on MapReduce, and it was really slow, and it didn't make any sense to do it like this. And so you couldn't really run something like Lloyd's algorithm. If you're taking the machine learning class, a lot of building these classifiers are similarly iterative in some process like this. You couldn't run these on MapReduce because you have to keep writing this stuff out to disk every iteration. And so this just made it infeasible. But on Spark, which doesn't require this, by doing some really clever bookkeeping so you can still recover from crashes, now on that system, you can run Lloyd's algorithm. You can run these machine learning algorithms. They have a framework. So this is not done on Spark. And then there's something called Shark, which is kind of a set of software that lives on Spark, and this has Lloyd's algorithm built in. It has a bunch of learning techniques built into this, right? So you can then call a lot of these techniques inside of this HDFS using the Spark setup. So this kind of changed the game a little bit. Okay, so let's see. So got 10 minutes left. I want to kind of mention. So I mentioned a bunch of stuff about rounds. So the one thing more about rounds, like if you want to do many rounds of this thing, you often need something like log n rounds, right? And log n is often a very small number, but if you do log base 2 of 1 billion, if you have a terabyte of items, key value pairs, you probably have maybe you have 1 billion things in there. Log base 2 of 1 billion is 30. 30 times writing to and from disk is going to be really slow. You're not going to want to do that. So we need something where you need log many iterations, which is very natural. If you look at these parallel algorithms, since the 80s, people have been developing, or earlier, people are developing all these algorithms. How do you do them in parallel efficiently? They often need like log n rounds to do them, and often optimally. And log n on a billion items is 30 rounds, and that's infeasible. So you kind of need to rethink about what you can and cannot do. Okay, maybe I'll get back through some other stuff, through some examples. Okay, so let me go through some examples of some MapReduce things, and you'll see that we'll say some things, and they may be something you could write a shell script to do on a small data set, but you can write a similarly small thing to do on a now hugely, massively parallel data set. So, okay, so we'll first start with with basically the hello world of MapReduce, which is the word count. And this is useful not only because it's simple, but it'll illustrate some point. So the input is the key value pair is going to be some document ID, and then the value is going to be just all the text on the document. So you can have a bunch of documents, and you have document IDs, and you have text, and the output is going to be for each word, I want the number of times it occurs. Okay? So if you're doing this on a single computer, you might actually sort all the words and then count them that way. If you're trying to do this in a stream, this is very hard to do in a stream. Right? You can't do this in sublinear space in a stream. There's some approximate ways of doing it, but they actually don't work as well as a lot of the other algorithms we talked about. In MapReduce, this is very simple. So for the map step, what you do is you create this from this doc ID and all this text. What you create is a bunch of these key value pairs where you have word 1 and a count. So the value is 1, and you get a word 1 here. You get the second word that occurs, you get a count of 1, and so forth. So you go through the document, as you scan it, you convert it into these key value pairs. So you just need to read it once. Every time you see a new word, you create a new key value pair. It's kind of, it seems like not very compact representation, but that's fine, right? Each word, and so the word is the key, and so forth, and then you just have to write this very simple mapper, and then the reduce step is the input to the reduce. Now you have some word, and you have this set of these values, v1, v2, up to vn. Right? And the output is going to be a single key value pair, which is the word, and it's just going to be the sum over all these values. Right? So this is all you do on the reduce step. You just sum up all these values. Okay, so this is how you do this word count. You're counting all the words in this thing. So this is, if you wanted to count the number of times every word in Wikipedia occurred, then this is probably, doing it on Hadoop is probably a good way of doing it. Right, so this is pretty simple. So what would not be ideal about this algorithm? What's a potential problem, though?
You have to send like a huge amount of keys over the network, so your network will be really slow.
Yeah, so I have to do that, but that's going to be pretty much unavoidable, right? I need to send, my data is all distributed. The word apple is probably going to occur if I only have 1,000 machines. Will probably occur at least once on every machine, right? So I have to send from each machine to every other machine something. So that's going to be kind of unavoidable to get all these counts. Yeah.
You can do that one optional step.
Yeah. So the problem, yeah. So I want to use. It's important to use one of these combiners. What happens is if I want to count the word the, right? The word this occurs like 7% of all words. Okay? So let's say I needed 100 machines to store all my data. that means I need 7 machines to store all of the thes, right? But I'm sending these all to one machine. It's not going to fit. If I do it like this, I convert them to these key value pairs. I try and send all these to one machine. They're not going to fit. And on top of that, you get this problem where it's called like the last reducer. Even if I didn't quite need all those machines, I just used them to speed up the parallelism. This one machine that had the word the on it is going to take probably 7 times as long as any other machine. So I have to wait for this last one to finish because it has so much more data than the other machines. Okay, so what I can do instead is I can do this combiner, and what I do is I just run a step first that takes all the things with this word and v1 through v2 up to vn. And I first do this, I do the same thing as on this reducer. And so basically if I have a bunch of documents on one machine, I aggregate, I count how many times the word the occurs in all those documents before I send it onto the machine that was keeping track of those words. Right? And then this same step, I was just summing these up, so it didn't matter that they were all ones or if they had other counts to them. And then this becomes so much more efficient. Right? So this is really important to do here. Yeah.
So the combiner works on a node level and not across nodes?
Right, so this goes on the mapper before the shuffle step. So this is a step, probably can't read that, but that's supposed to be a 1.5. Right, this was a 1.5 step. So the shuffle is 2. Before you run the shuffle, you can run a combiner.
So it doesn't go across machines to combine, it only combines on the one.
Yeah, it's going across machines at the reduce step. Right, that's where you do that. So this is before you send it off to the network. So you don't have any control really of how it's flowing across the network. You want to compress it before it gets sent across. You could also think of, if you're doing some of these streaming algorithms, sometimes you can compress your data with the combiner before you send it across the network, and this will save on the network cost as well. Okay. So another kind of big task, and this was one of so there are 2 kind of main tasks that Google needed MapReduce for. One was PageRank, which we'll talk about on Monday. This will be a bit more complex. But the other one was creating this inverted index. And so this is like storing, if I search for a word in Google, what are all the pages that the word is on? Right? So basically what I have is all these, the input is all these pages, and they have these words on them, and what I want to do is invert it, so I have words, and I list all these pages that the word occurs on. So this is what I want to, this is why it's called the inverted index. This is typically how things would be stored, and I want to invert it, so when I have a word, I know all the pages that has this word. It used to be that some words, so then I can quickly look this up, right? It used to be that some words would occur on only one page, and Google would only return just one result. Now it manages to fill the 10 possible pages with something. And so again, this is very simple. So the map step, I go from a page and these word 1, word 2, up to word n. So this is a set. And here, and I output instead word 1, page, word 2, page, and so forth. Right? So I just invert this single key value pair into a set of key value pairs. Inverted, and then on the shuffle step, I have this word, and I have all these pages. And so I just do word, and I take the union of all these pages. And so that's all I do. And if instead of this union I could sort by some score. And if I wanted to maybe along with the page, I had other information like the page rank of that page or some other stuff, the score. That page rank could get passed along in the value here, and then the score could be some function of that page rank, as well as maybe some other stuff about the page. And so then I could sort them by the score as well. So then I know that the top 10 things are what I'm going to show on the page with the search results. You can build this into the reduce step. Oh, sorry, this is not shuffle. This is reduce. Sorry about that. Right? So these are all you need to write. You only write this map step and this reduce step, both very simple. The back end is doing all of the shuffling, which is complicated for you. If some machine goes down, it realizes that machine's down and it reroutes the computation, either the mapping or this reducing, to another machine. Right? So if it goes down during the map phase and it's not responding, there's some master node which is occasionally pinging all the machines. If it stops responding, then it tells other machines that have the same data to redo the map step. If a reduce step, it stops responding, then it tells all the machines that mapped the data before to that to map it to a bunch of other machines, and they recompute it. Right? And so it can redistribute it because the key level is much smaller than what's on the machine. There are many keys on the same machine. Okay, so there's another example I have in the notes I won't have time to go to, but the idea is you have this big static data fit across many machines, and typically you want the output of it to also be large. If the output is a single value, I just want to compute the sum of all the words, the number of all the words I have. MapReduce, again, is probably overkill. But again, if note, in all these examples, the input was big and the output was big. And the MapReduce solves it. It reduces it to a couple of easy programs, and it builds in the parallelism and the resilience in this. Okay, so we'll see a much more complicated example on Wednesday on how to do PageRank. And this will bring in some other kind of interesting large data scalability ideas. So turn in your final reports through Canvas. We'll talk about posters on Wednesday.
Is that still recording?
Yeah, do you want me to turn it off?
Yeah, it's